Good morning. I would like to get us started. Thank you all for coming. I'm Lydia Kavraki. I am a professor of computer science at Rice University, and you are in the Task and Motion Planning from Theory to Practice workshop. Again, thank you all for coming. I think we have a wonderful program. I have, two purposes for standing here. One is to welcome all of you, which I did, and the second is to introduce the co-organizers of this workshop. So this workshop is co-organized with Neil Dantam. Neil is an associate professor at the Colorado School of Mines. Ken Elimelech, Ken, stand up. Ken is a postdoctoral research associate at Rice University. And Federico Pecora, Federico is with Applied Sciences at Amazon Robotics. And as you see from the schedule that we had up, we tried to invite a set of people who cover task and motion planning in academia, but also people who will give us a different perspective from the industry. So at this point, I would like to invite Neil Dantam to make a short introduction, and we'll get started. Thank you all.
Okay, thank you, Lydia, and thank you all for joining us today. So I'll give a little bit of maybe an overview of task and motion planning and some of the context and challenges that different people have worked on, and then I'll say a little bit about what we'll have in the workshop today. So, here is a classic planning problem, blocks world that had, back in the 70s, some elements of task and motion planning. So we took this manipulation problem, you produce a discrete abstraction of this that's describing the relationships between blocks in this simple manipulation setting. So the focus initially was on the discrete planning part, but it was an abstraction of a continuous manipulation problem. So what do we mean when we say task and motion planning? Task may be one of the most overloaded terms in robotics. So what we are typically meaning by this, task is the discrete or symbolic or classical kind of planning, and motion is the planning in this continuous or geometric space. So that's what the kind of problems we're trying to capture here. Classically, task planning is dealing with these discrete transitions. So you can think about this as some enormous transition system, and we're trying to find a path through here. Motion planning, right? We're trying to find a plan from a start to a goal in this continuous configuration space. Okay, so how do we put these things together? Here is a partial roadmap of different planning approaches. So approaches for doing task planning. Heuristic search works very well. There are some nice constraint-based methods. Logic programming approaches are closely related. For motion planning, these local or optimization-based approaches were popular, a couple decades ago, and are popular again now. Sampling-based planning gives you these nice robustness guarantees, and then there are heuristic search approaches as well that work in certain domains. So maybe if you are looking carefully, you'll see the word heuristic on both sides of the screen. So aha, we found the thing to do for both of these. But really it comes down to the details of how you're searching these spaces, right? So even in your sampling-based planners, you have different kinds of heuristics. So it's a different space for the discrete side versus the continuous side. And we have all these specialized kinds of planning search techniques. So how do we put them together? And then some in the audience are probably thinking we need another bubble here for learning. So maybe this is a question to discuss over the day. All right, so how do we do task and motion planning? Well, I guess the obvious thing is you take your problem description, you first do task planning, we get a task plan, then we do motion planning, we find our task motion plan, and then the end. Everything works fine, that's it. Okay, that's not quite how it's gonna turn out. And we'll see, I'll talk about some of the challenges that we tried to address in the academic world, and I hope some of our speakers will talk about some of the practical challenges that they're focused on. So here are a couple of foundational works that are explicitly calling the problem task and motion planning. So the Asimov planner, you can see, is combining these different kinds of planners. So task planning based on metric FF, coupled with motion planning, right, trying to close the loop between these two. And then Kaelbling and Lozano-Perez, their hierarchical planning in the now is interleaving task and motion planning and execution to try to deal with these longer horizon kind of problems, both very influential works in the development of task and motion planning. So this is a list of challenges that various academic researchers have focused on in task and motion planning. And potentially there are more, but these are the lists that we were able to think of. So first we want to specify what it is we're trying to solve, and this itself can potentially be a challenge. Dimensionality is an issue. So task planning is hard, motion planning is hard. You put them together, and it becomes harder than the sum of its parts. Then you have coupling between your discrete and your continuous space. So discrete decisions influence the continuous decisions you can make, and vice versa. Completeness, right, being able to determine if you have a plan or not, is especially challenging in the motion planning world. And then potentially we want optimality in the plans that we're producing. So a question for the participants is, which of these are the important challenges, or is there something not up here that's really the important challenge? So I hope we can think about that over the day. All right, so classic ways to specify these problems. For planning domains, the planning domain definition language is kind of a de facto standard for how you describe a task planning problem. So you have this first order logic description of the state, you have a start state and a goal state, and then the changes you can make, the transition function, we describe in terms of actions with preconditions and effects. And so this is still the textbook blocks world example of a task planning domain. So also popular in the robotics world is our temporal logics, and maybe especially linear temporal logic in some related forms. So LTL is taking our Boolean logic that we all know and adding these temporal operators, right? So something, a formula that has to hold at the next time step, one formula that has to hold until another holds, one formula that holds at some point in the future, and then some formula that always holds. So if you have a state you're describing as an assignment of Booleans, right, LTL is describing the change in that state over time. So for many kinds of domains, this is a convenient way of describing, specifying your system. Okay, and then to specify a motion planning problem, we have our configuration space, and for manipulator, we'll typically describe this as a kinematic tree or scene graph, right? All the joints in your chain. So the old way to do this was with DH parameters. The more modern mathematical way is with the product of exponentials, and then there are file formats like URDF and Collada that are capturing the same kind of thing. Different approaches people have taken to couple task planning and motion planning. So one approach is to do your motion planning up front and produce some kind of discrete abstraction or roadmap, and then do task planning over this roadmap plus maybe some additional discrete requirements. Another approach is to call motion planning as a subroutine, or sometimes called a semantic attachment from your task planner. And then if you find a plan, find a motion plan, it's feasible. And if your motion planner times out, then there's an assumption of infeasibility. And then the last approach is some kind of iteration between task planning and motion planning. So finding a task plan, trying to do motion planning, and if that doesn't work, using some feedback to update your task planning. Completeness of motion planning is a problem I've been thinking about, I realize, for almost a decade now. So classically, our sampling-based motion planners are probabilistically complete. So that means if a plan exists, we find it in the limit under some assumptions about clearance. But if no plan exists, right, what do we get? We get a timeout. right? Because they would otherwise run forever. So this poses challenges for task and motion planning. We have some task action. We want to know if it's feasible, right? Does a plan exist? Well, our sampling-based planner is going to return a plan, right, if one exists eventually, or it'll time out. So what does that mean? Using these probabilistically complete planners, we could not prove that an action is infeasible. So this was an issue in task and motion planning, right? Do we spend more time trying to check? Maybe we just need to grow our search trees a little more, or should we move on to other things? And this limitation had a strong influence on how we would develop task and motion planners, and influenced our work. So I came onto this, 2014. We had a publication in 2016 combining constraint-based planning with sampling-based planning. And so we had these nice capabilities with constraint solvers to incorporate additional information from the motion planner, using these timeouts as some approximate indication of feasibility, and then iterating between task planning and motion planning. And then there were some different variations on this approach of iterating between task planning and motion planning. And if you do this in the right way, you're able to get at least probabilistic completeness of your task and motion planner, but potentially at a large cost of doing a lot of planning, motion planning work. So optimality in task and motion planning is an additional concern. So Mark Toussaint takes this optimization-based approach, right, combining integer optimization and trajectory optimization in logic geometric programming. Will Vega Brown and Nick Roy, their work is on asymptotically optimal task and motion planning, using piecewise constraints on the system. And then Will Thomason has done some work on using sampling-based motion planning, so based on the observation that your optimal task plan in isolation, your optimal motion plan in isolation may not be parts of the optimal task and motion plan. So largely addressing this dimensionality, scalability in task and motion planning, we can potentially be spending a long time trying to refine each of these task actions, finding motion plans for it. So maybe there's a cheaper way to do it. We can train a classifier for motion planning feasibility, right? And this gives us an approximate indicator of feasibility, right? It's much faster to run a classifier, get a quick answer on whether a plan is feasible or not. You do this in the right way, you can significantly improve the performance of the task and motion planning system by avoiding at least some of that motion planning effort for infeasible plans. So coming from that, we spent a lot of time trying to really take this challenge of probabilistic completeness by the horns and saying, can we do better for the completeness of motion planning? And have developed this idea of proofs of motion planning infeasibility. And turns out we can strengthen the probabilistic completeness guarantee to what we call asymptotically complete motion planning. So now in the limit, in both cases, right, both feasible and infeasible, you converge to finding either a plan or a proof of infeasibility. So I think this work may change a little bit how we start to think about this coupling of task planning and motion planning. Oh, and if you couldn't tell in this example, right, what the right scene is the one that's feasible. Okay, and then Ken has approached the scalability challenge in task and motion planning by trying to learn abstract skills for one kind of problem and transfer these to another problem to reduce the amount of planning effort you need to put into these different scenarios. So there's a brief history of various work in task and motion planning, how different groups have tried to address some of these different challenges. So where are we now? This is what our sixth workshop on task and motion planning. We started just up the road in Ann Arbor, so had kind of general workshops for a couple years, and then by 2018 there were a number of researchers who had begun publishing in this area. So we thought, well, let's try to figure out how we can compare these different task and motion planning approaches. We'll develop a set of common benchmarks, have this exhibition and benchmarking of task and motion planners. A couple years after that, we tried to broaden a little bit, so robust task and motion planning focusing on dynamics and uncertainty, seeing how we can incorporate learning in task and motion planning. So after that, we took a couple years off for the obvious reason. Now we have a workshop on task and motion planning from theory to practice. So I guess this is kind of a reflective workshop. There's been research in task and motion planning for almost 20 years now. So what is the progress that's been made in this academic research? How well is it solving the practical problems that we are aiming to be solving? Are we addressing the right challenges? Are there other challenges? Where are the gaps that'll have the practical impact that's supposed to be the point of the work? So I hope there will be some good discussion on this topic today. So here's our schedule for the workshop. We have seven invited speakers, a mix of academic speakers, industry, and government. We'll have lightning talks right before lunch, a poster session right after lunch, and then I hope many of you will stick around for our discussion and wrap up at the end of the day. So, and then here's our list of posters. We'll introduce these during the lightning talks. So I think now I will introduce Ken Elamelik, who will introduce our speaker.